Hello. Let me share. Okay, so this is our lab assignment. As you could see, this is a circuit with 3 nodes that are independent, and then there are, our common node or the reference node. So nodes ABC have been marked as the independent nodes, and you can the bottom node just below the 5-volt source, you can mark it as a reference node, which is common to the 10-volt as well, and the 10K resistor, which is the R5. So this is and of course the 2 other nodes which are between the resistor, for example, R1 and V1 voltage source. So we know the voltage there. So again, that is not an independent node. Similarly, the one between R2 and V2, that is also not an independent node. So therefore, you will have, for the first part of this problem, under the procedure, it's a pretty straightforward experiment where you have to solve the problem by hand first, and then verify the results that you came up with in the part 1 through the simulation. So for part 1, we'll come back to that in a moment. But I mean, the process is pretty obvious. I'll just kind of spend a few minutes on that. Let's just talk about that first, and then we move on to the simulation part. So okay, so you can label these nodes. We can label the current, since we're asked to do the node voltage analysis. So we'll apply the KCL at node A, B, and C. So I'll just assume this current coming in this direction and then moving in this direction. Similarly, we can say that this current is going like that. And I mean, of course, if the directions don't appear to be correct, you will have some negative numbers, which is going to correct these values. So we can label these currents. So I'll call this one I sub 1, this one is I sub 2, this one is I sub 3, this one is I sub 4, I sub 5, and I sub 6. So let me go ahead and write just an equation for one of the nodes. So if we look at node A, we can say that the current coming in to the node is a positive value, and currents leaving the node are negative values. And the sum of all that is going to be 0, right? So when you expand on this, what we have is we can say it's 5 minus V sub A over 1 kilo ohm resistor minus V sub A minus V sub C or 5.6. I mean, this is K also. Just use the space here. And this is for I3, by the way. So I2 is going to be same way. I'll just write it here. That's going to be V sub A minus V sub B or 4.7 K. And all that is equal to 0. And then you can expand on this and, solve for, so you'll have three equations, three unknowns. Same thing you will have in the same way at node B and node C, you will come up with the equations. And then you can solve for the three unknowns. And based on that, then you can verify the results. Now, going to the simulation part, you're asked to, so over here, we've been asked what is the voltage here, and here, and also the current. So based on whatever your calculations are, you will determine these values. And then to verify them, you'll do the simulation here. Okay, and then you plug in the values for all of these. So let's work on this part today. And for that, I'll need to stop this share here. Okay, so this is, I've opened up this multisim.com tab. And what you need to do is you will go to creating the circuit. And here we'll pick up all the required components. So I'll assign the values in a moment, but let me just set up this generic circuit first. Okay, so you may want to label them in the same way. I just, I started from the top, so let's just kind of go back. It's just to make, this is R1, R2, R3, R4, R5. Okay, all right. So let's go back here. I'm sure we can label these. Yeah, I think we can change the label. It's much easier this way. So this is R1. Okay, let's just call this R7 for now. And let's just label this.
I think you could just grab them and switch them instead of relabeling them.
I think that's maybe a good idea also, but I just have to change the orientation of those. That's another. Okay, so now I have R1, R2. Let's just see. And then this one is R3 and R4. Okay. Okay, so since R4 is not there, and I mean, we don't have that label anymore, so I can should be able to label this. And this one is R3 there, and R5. Well, that just worked out that way. But again, of course, there's different ways you can go about it. But I just wanted to be consistent with the with our representation in the lab assignment. Okay. All right. So let's go ahead and place the two sources there as well. So we'll go for the DC source. Okay. And let's make the connections.
What did you click on to get the DC source?
Oh, the DC source. Yeah. So I went to
Round
this.
symbol? That, okay.
Yeah, that where it says sources. That's the third tab in that menu. So over there you have a bunch of sources, and you will see the DC source there.
Got it.
Right. Yeah, and one other thing
I'm doing it with you, so I'm not as fast as you, but
we'll work at a consistent pace with each other. And one other thing you could do, just normally the way we so we are used to this symbol, like the circle with a plus and minus. So either one of the symbol would work fine. They both represent the DC voltage source. So, I'll just leave it up to your preference. Either way, you could do that. And the way to change it is just by clicking here. And once you click there, then you have this symbol option, and you can select either one of the two. Okay, I'll just leave it like this. All right. So are you able to have your 6 resistors and the 2 sources?
yeah, my screen looks exactly like yours.
Okay, wonderful. So let's go ahead and make these connections. So if you bring your cursor to either side of the component, at some point you will see this. It's a little bit difficult. It's just a small area of pixels where this symbol would appear. So you pick this and then essentially make the connection where you want. And whenever the connection is made, you'd see this decreasing circle pointing to the location. So you just click there. And once you do that, that connection is established. The other connection, we can do it on the other side, and you can sort of do it in the same way. And sometimes they may not be perfect, just like this one. So I'm just, if you want to redo it, even though it functionally, it's not going to have any impact, but visually it just makes a little bit difference to write it cleanly. Yeah. You had a comment or question?
Nope.
Okay. All right. So we go there. And if you click where you want to sort of make a turn that will allow you to make the turn. Just, for again, aesthetic reasons. So let me just look if I'm missing something. I don't think I do. So yeah, and I'll just make the last connection here. Okay, so our circuit is settled as far as the layout is concerned. Now we need to have the correct values to all the components. So let's start with the voltage sources. So V1 is 5 volt DC and V2 is 10 volt DC. So V1 by default is assigned 5 volt value. For V2, you can change it to, so if I click on this, I can change the magnitude, or if I click on the 5 itself, it'll give me this this option to change the value, and I can change it to 10 volt. If you need to change it further, you can also do that by the menu, by clicking on the voltage source, and this menu should appear on the right hand side, and over there you can change the value. For example, if I wanted to go, let's say, to 100 volts, it will be changed, right? Just like this. So, but I just want to keep it at 10. But again, sometimes some of the problems may require you to have larger voltage sources, which this shortcut symbol does not allow you to do. So, but this is 10 volt and 5 volt here. Now we need to set up our resistors to the correct values. So let's start with the top resistor, the R6. So R6 is assigned 5.6 kilo ohm value. So I'll click where it shows its magnitude, and from there I'll select 5.6 ohms, 5.6 kilo ohms. Okay. Just have to. Okay, I got it. So this one is 5.6 kilo ohm. Then R3 is 4.7. And you can also enter it in the magnitude there. So there are different ways you could do that. So you can do it on the menu there on the left-hand side. Just plug in the value, or you can use the sliding tool after you click. So I mean, the different options there. And the R4 is 6.8. So again, I'll select this value from this side. R1 and R2 are 1 kilo ohm, and R5 is 10 kilo ohm. So we can go ahead and assign these values. So now, as far as the simulation part is concerned, that's pretty straightforward. Unlike the digital circuits that we used in the previous course, where you had to connect LEDs or other ways, all you have to do here is connect probes at different locations. So, for example, here, you can label these nodes also differently. So over here, I have actually these are the wired connections, but so let's go ahead and assign voltage. So again, you have okay. So now on the very top option in the list of components, you'll see this green circle with a V in the middle, and sort of a probe connector being showed there. So if you click there, you'll see these different tools for our analysis. So you can have a voltage source, you can have a current, voltmeter is what it's being shown here. not the source. So you can have a way to measure your voltage, a way to measure your current, a way to measure both voltage and current. So those are the different tools available there. If you are going to be placing a component, or if you're going to be checking the voltage at the node, then you cannot use the V/A. The reason is simply because for that, at the node, the current is essentially not known. So you'll have to be on one side of the node. So therefore, I'll just, for the nodes, I'll just place these probes to measure my voltage. Okay, and you can just duplicate it and place it in different locations. Okay, now R6 is of interest to us. So what I will do is, it is asking me to measure the current that is going through R6. And of course, I mean, you have the green and blue colored voltage probes, which will tell you the difference in voltages, and you can, verify from there, or you can directly check these values by connecting the probe to the appropriate branch of the circuit. So now I have all these connections made, and I've also connected all the probes to the appropriate locations. So let's take a look at so we've been asked to do, the node A voltage, node B voltage, node C voltage, and the current in R6. So all that has been connected. So let me go ahead and go to this run icon, which once you bring your cursor there, you sort of hover your cursor, it's going to say run simulation. So you click there. Okay. And over here, you can now see your different voltages. You can also see the current there, right? So that's how you can verify your different values. The other thing you can also do, okay, there's one warning, by the way, so we don't have a ground connected, which can be an issue. So let's go ahead and connect our ground. So I mean, that's an error. So the ground, if you go to this component list, you'll see this in the second tab, and you can select this ground and just connect it to anywhere on the reference node, and that should be fine. And at this point, then I can go ahead and run my simulation. You can see the values have changed significantly. So now this is and this is all you have to do as far as the simulation part is concerned. And if you were to do it in a lab setup, what you would need is 2 voltage sources connected in the manner like this, and then be consistent with all your nodes. And if you had a DMM or a oscilloscope, you will connect the probes of those devices, those measurement devices, in such a way to be able to measure these voltages. By the way, these voltages on each of these nodes are measured with respect to the ground, right? So if you were to do it in a lab setting, you would connect one end of your, basically typically, I mean, the active one on the node, and then the other one on the ground. Obviously, the devices are marked that way also. So you would use it in this manner, and everything is going to be measured with respect to ground. So this is how we do the setup. Are you able to get the same result?
Yeah, I've got the same thing in here. So the numbers we're getting on this Simulab, that's going to be our measured column,
That is
right?
correct. That is
Okay,
correct.
and then we're still going to do the hand calculation.
Yeah, the
as
hand
well.
calculation, you sort of, just like 3 weeks ago, the node analysis that we did. So you do the same thing here. So
Okay.
for the and then what you will do is it allows you to verify your results. And one thing additional you could do here is, if you want to see the level, you can look at this 3 options there. There's a schematic option, the grapher option, and the split option. The split option will show you these different levels. So now you could see that I don't see any of my voltages here, and the reason is this, that my reference range is basically these values are beyond the reference range. So let's look at what are my reference ranges. The reference range you can increase for the voltage. So the maximum voltage range has been defined as 3.5. So, and all my voltages are above 3.5. So if I go, let's say, to 10, I should be able to see my 3 voltages. Similarly, for the current,
I'm unable to get the same. Like I was able to hit split, and then I'm on, there's items and documents. I'm on items, but I don't have anything. It says no items selected. Do I need to click on something, or?
So are you running the simulation
Yeah,
already?
it's running on the left.
It is running on the left.
Yep.
So if you click, do you see the interactive one that is being shown on my screen?
Yes.
Do you see that? Okay. So now you click in the middle of this, anywhere on this graph.
Okay.
Okay. So you'll see that menu on the right hand side.
Okay. Yeah. Now it popped up. I got you.
Yeah, and then you kind of scroll down to the lower part of this, almost to the bottom, and over there you can select your range for the voltage. You can select your range for the current. I mean, I can select a 0 here for the voltage. So minimum is 0, highest is 10. Similarly for the current, since my current is 600, it's less than 600 microamperes, so it is selected correctly. Essentially my current is this dotted line, and then the solid 3 lines, which are again corresponding to the colors of the probes that are connected to the circuit.
Okay.
So in your lab report, it'll be worthwhile to sort of have a screenshot of this graph also, and you can see this separately as well. If you want to get a bigger views, just click on the grapher side. If you look at the schematic part, you just simply do the schematic tab, and if you want to see both, then you do the split, right? So the various options to view it. And if you want to change any of the reference ranges, then of course you just sort of click in the middle of this graph and select the range that you want to display. So but I'll just get rid of this menu just to increase the size of this screen here. All right, so I think you can save this circuit. You can export it or take a screenshot, whatever you prefer, the way you would attach to your lab report. It's a pretty straightforward lab report. I mean, there's not a lot of analysis, but what you would record there is just, what your approach was. You do your hand calculation, you write those data, and then compare them. So this is just the way we would do the simulation analysis like this. Okay, let me go ahead and stop my simulation. And if you want to modify your circuit, you cannot do it while the simulation is running, of course. So once you stop it, then you can make any changes that you want. But what it will do is it'll show you the last recorded values on your probes. So, so that's just the general idea of using simulation in this course. Any questions about anything here?
No, this is awesome. This is
Okay. Yeah.
This is great.
Yeah, I think it helps when we work together. Again, in the regular lab setup, we also there's actually more time there also, but obviously the creating the circuit by hand also takes a little bit longer. But rather than doing it on your own time, the lab assignment, I think it's good to do it in this session. The reason is simply that any questions are, rather than spending a lot of time being stuck on some point, the questions can be addressed right away. Okay, so okay, with that, I'm just gonna stop this share, since looks like you are in good shape with this. So let's go back to our Are there any questions about the exam, which is going to be due tomorrow?
No, I already turned it in, so
Okay.
I think I taught myself a lot. I didn't know that when you change it from volts to amps, you change the resistor from series to parallel.
Right.
I didn't know that. So there's a lot of stuff in there that I don't know. Some things I got, I probably got it wrong on question 2, but then I got it right on question 4 because I just kept kind of fighting it the whole time. So
right.
hopefully I did good. And like
Yeah.
I said before, in previous, classes, if I'll take a bad grade so long as I know what I did wrong and what's the correct method. You know what I mean?
Okay. So what I will do is maybe after I return your assignment, also make some point, basically some remarks on your, the graded assignment. But maybe I spend a few minutes just to solve the problem here, or if there's a minor change that is required in your approach, I'll mention it on your
Okay.
and
I don't mind if you do it in class either. I mean, if like you said, if someone else is, if I'm making the same mistake, perhaps someone else is too.
Correct.
So I don't mind putting me on blast.
Yeah, and I think it goes a long way. Just like just like we discovered in this lab exercise that so we spent maybe half an hour on this, but it really registered with you. And I think if you want to use this tool again in the future, you should have a pretty good grip on it. I think that is useful. And the other thing is that I'll do the same thing with the exam. So I'll just maybe hopefully I can grade it over the weekend, and then I turn it back, the graded assignment to you. And on the start of next session, we'll just spend a few minutes just to go over the areas that need some attention. Okay. So yeah, great. All right, so let's talk about the next topic. The next topic is so we're going to be discussing some theorems that are used for circuit analysis, and one of the important one is so these are two different ways to look at it, but in short, they're combined and they're called Thevenin and Norton theorem. So before we really dig into that, those are basically named after two engineers who this basically explain this technique of circuit analysis. But before we do that, we need some foundation to go analyze circuits in these techniques. So I just want to revisit a few topics here. So the ideal voltage source, you want to go back there. So the ideal voltage source looks like this, as you know. In the ideal voltage source, there's no source resistance, right? So it's just a it's a perfect, it provides the entire voltage to the whatever load is connected there. Now, there is one limitation with this ideal voltage source, and that is if this load that we are connecting to it, if it approaches zero, okay, what will happen to the current that is flowing through this? Let's say if it is some, source voltage, and the current that is flowing through the circuits, what will be the value of this? It's going to become smaller and smaller. Let's say if this load resistor reaches zero, then if I have to derive the current, so of course we have V is equal to IR as our Ohm's law, and I is equal to V over R. So plugging in these values, this circuit will have infinite amount of current, which is not realistic, right? So there's no such thing. No matter what the voltage source is, you cannot produce infinite amount of current. So therefore, this is called an ideal voltage source. It's not a practical voltage source. We cannot use it. In order to basically this anomaly, or one of the conditions where your load is zero, so account for just to sort of counter for that, what is done is, along with this Vs, in series, a source resistor is used, and it's typically the value of the source resistor is a small value. In reality, in real voltage sources, there are some components within a voltage source which provide some resistance, and that is modeled as a source resistance. So therefore, that source resistance is accounted for here. And from this point on, then you can connect your load. So if RL goes to zero, you still will have some finite amount of current going through this circuit, which is going to be represented by this source resistor and source voltage, Vs. So that's one of the conditions that under which we cannot use the ideal voltage source. So therefore, you will have to have these source resistors. Now, same thing would happen if we have an ideal current source. So if I have an ideal current source, okay, so here, this is represented by this arrow. And then you have this load resistor. Of course, you can mark your terminals here. So I have a source current going through here, a load resistor. So in this case, it's going to be opposite, right? So if the load resistor is approaching infinity, okay, and what will be that? I mean, it will be just an open circuit essentially. So if you have an open circuit instead of the load resistor, then you have infinite amount of resistance between the two terminals that you are connecting. So essentially, what in order for you to bypass that infinite resistance, you need to have a very large amount of current to ionize the essentially the air that is in between the two terminals. So, which is obviously you may not have that amount of course, we don't have that amount of current to do that if it's a separate, if they're separated far enough. So therefore, what we would say is, as a result of this, I sub s is going to be infinite. So therefore, what we want to do is also have a practical current source, and the practical current source will look like this. So it will have a source resistor in parallel, and then you connect your load resistor like that. Okay. So always remember that in this format, what it will do for us is, even if we have this as open circuit, let's say the connection is not there. Let me just rewrite, otherwise it's gonna erase. So this is I sub s. That same IS, the integrity of IS is going to be maintained. Okay, so that is going to continue to flow through that RS, and even if we don't have, if RL is equal to infinity, or it's essentially open circuit like that. So therefore we use the voltage source and the current source in this manner. Okay, so what if we had, instead of having this in parallel, just because before we had in the ideal, in the practical voltage source, we had it in series. So what if we do it in series? So that'll be the question. So why do it in parallel here and series over there? And let's look at the reasoning for that. So what if this is my current source, and I connect the resistor it's not going to help me, right? Because having this series resistor in series or not having at all would still have have no impact on solving this problem for me. So the only way it can solve this problem for me is if I have this in parallel. So therefore, that is an important distinction that you can make, that why you have this in parallel versus this one in series. Okay, so let's see.
Does it just switch, or is current always parallel and voltage is always in series?
So the voltage is always in series with the source resistor, and for the current source, it is going to be in parallel.
Okay,
I mean, that's the way it is connected.
because there were some problems where they'll show a resistor in series and then another one in parallel. And when
Mhm.
you convert it when you go from voltage to amps or voltage to current,
Mhm.
it only moves one of them. It doesn't flop them all, or I don't know if I'm saying that right, but
Yeah, so typically you would see this representation, right? If you see, let's say, a representation where a resistor is connected in series with a current source, then that you cannot apply source transformation to that, right? So, for example, you may have some circuit but there'll be other components within that circuit. So the only way you can apply that is, for example, I have some rest of the circuit like that. Now what you will do is you will resolve the right side circuit. So you have this series connection between the, let's say, R1 and R2. So you combine them, you add them together, then whatever that R1 plus R2 is, you take the parallel combination with R3. And once that is resolved, what you will end up with is this. So you have to maybe take multiple steps in order for you to get to the right position. So in this case, you have this, this will be your R equivalent, and then you add it together. Even then, you will not be able to convert it to a voltage source. The only time you can convert it to a voltage source, the source transformation, is when you have the resistor connected in parallel to the current source, or resistor connected in series to the voltage source. If that is the case, only then you can do the source transformation between current and voltage.
okay, so it's just the first one that's in series with the voltage source.
Right. Okay. So this is the correct representation. Now, if I want to say I want to apply the source transformation here, I can do that. So what I will do is I will convert this. Let me just go ahead and
yeah, so I'm hoping I got question 4 correct on the midterm exam then, because this is kind of what we're discussing, and I've already turned it in.
Yeah. Okay, so I'll review that and I'll see your approach, how you have done that. But I mean, over here, you can derive your magnitude like that. And then if you did it like this, then it should be correct. If I recall correctly, for that one, you have to transform the one on the right-hand side, I believe. If you do that, then both become voltage sources. If you transform the one on the left-hand side, then they both become current sources. And then you can also solve it that way. So both techniques could be are equally valid. It's just that you just have to, in one case, you will apply the KVL. In the other technique, you will apply the KCL to take the sum of the different voltages and currents respectively. But both techniques will work. So I'll spend some time after the due date is passed for the exam. Okay. So let's just talk a little bit more about these practical voltage sources under load condition. So we briefly talked about how we can connect the load to that. But let's say if I have this, again, you are familiar, it's most likely going to be a review of the previous concepts. So So I have this source resistor connected here, and then I'm going to connect a valid load to this. And if you're asked to determine the value of this load resistor, so what do you think? What will be the? Of course, there is a multiple options in which you can solve this problem, but what will be a straightforward technique in which we can find V sub L? Okay, so in my opinion, you can apply the best option is if you would have known the value of voltage across this, well, I'll just call it V sub RS. If this is known, then of course you can use the KVL in this loop. But the best option here is the voltage division, right? So voltage division, all I need to do is the source voltage, and then I'll just write the generic formulas here, but again, you will have some practical values if the problem can be solved. So of course, the sufficient number of known values will be present, and then you will have RS plus RL. Okay, so this is going to give you the value for V sub L. Same thing if you consider the practical current source under load condition. And you have a load resistor here. And let's say if I'm still asked to solve for VL, then it is a multi-step problem, okay? Because I don't know how to solve this. I don't know how, the only way I can look for V sub L is if I know the value of R sub L and also the current that is being passing through that R sub L. So then I will say that, okay, V sub L is equal to, I'll just call it I sub L, R sub L, right? So if I know the value of this quantity, I still have to find this, right? So if I want to find that, and I have I sub S known, and RL is known, and RS is known, but the things that are unknown are these I R sub S, and I'll just call this, let's just rename it to be consistent. So I need to know this current. Okay, this current need to be known. So these are the two unknown values for me. Let's say the resistance and the current values for I sub S and RS, RL are known. So I can use current division to find this value. Okay, so what is the value of current division? I will take whatever that source current is, and then I'll apply the conductance technique. And of course, you can do the other options, but over here I will use the conductance of RL. I mean, this is just a formula for current division, and in the denominator I will take the equivalent conductance. So in this case, I know this value, I know this value, I know this value, so I should be able to find RL. And once I do that, then I can say VL is equal to I sub S 1 over R sub L or 1 over R sub L plus 1 over R sub S, and then apply the R sub L there. Okay, and then of course you'll solve for that and you'll have your VL value there. So this is one other sort of example there. As you would notice in the exam also, that sometimes the repeated use of source transformation helps to simplify the circuits, right? Particularly if you have multiple voltage sources, it will help in simplifying the circuit significantly. Again, going back to the Thevenin and Norton concept, ideally you want to, there's a specific technique that we'll discuss, but ideally you want to bring your circuit to one of these forms. Okay, so you want to have your equivalent resistance of the entire circuit. So there may be some complex circuit that is provided there, and then your voltage, or you want to bring it again to the other form, like this. Of course, they have specific names, and we'll discuss that later. But again, this is some current. So this representation is called the Thevenin representation. And this one is called the Norton representation. Okay. And they can be transformed between one another. So they are the two techniques in which you will find the values there. So this is basically a way of representing a very complex network in a very simplistic manner. So that is important there. So let's look at, before we move on, I just want to make these 2 points there. So you want to make sure that for source transformation, the okay, and okay, so example of that would be, let's say I have a voltage source like this. And sometimes you'll have to go through multiple steps to have it connected in series. So let's say you simplify this circuit to this format. Now what you want to do is you take the sum of these two voltage sources, and of course the polarity is different, so you'll have to take the difference of the two and use that, and then you will have your R1, R2, and R3. So this one is, let's say, V1, and this is V2. So V sub S is going to be the sum of V1 plus V2, and R equivalent is going to be the sum of R1 plus R2 plus R3. so that if you bring it to this form through source transformation, and of course I'll show you some examples there, uh, then you can simplify it in this manner. And the goal is again to bring your circuit to one of these two representations for analysis, right? So for that, we will try to combine everything that can be combined. The other process with the current source, let's say if I have I1 here, and so at this node, both of these currents are coming in this direction. So if you can, you will combine these two sources, I1 and I2, into a single source. So one way you could do that is if you transform this into a voltage source, which means that this resistor R1, R2 is going to be in series. At that point, then you can combine the resistance. Actually, that won't be the best approach, but you can apply essentially the KCL at that node, and determine the value, since it's a single node here. Let's look at some examples here. I think that'll be a better way of verifying this concept. So let's say if I have a current source here, a voltage source here, this is 2 ampere, this is 34 volt, and there is another current source, which is 1 ampere, and there's some current flowing through this 1.5 ohm resistor, which is called I sub 0. So we need to find that. I mean, so there will be some, just like you know that in different exercises and questions in the textbook also, there's some unknown quantity that is labeled in the circuit, and you're asked to find that. So this would be an exercise in source transformation. So what I would do is I'll convert the two current sources to voltage sources, and then try to combine them together. Okay, so let's do that. So the next step from this is going to be this 2 amp and the 6 ohm resistor being converted to a voltage source, and the polarity is determined in this way that the direction in which the arrow is pointing is going to be your positive terminal of the battery. So that's why, since the arrow is pointing to the top, therefore you have the plus on the top. The 6 ohm resistor is brought to the series, and this is the second 6 ohm resistor. And in this case, we have this current source being converted to the voltage source, and it has a resistor there. Okay, so let's go ahead and label these. This is a 1.5 ohm. This is 17 ohm. Again, this is still our unknown quantity. 34 volts for this. This is 5 ohms, 6 ohms, 6 ohms. So let's determine the magnitude of our voltage sources. So we know that V is equal to IR. The current is 2 ampere. And is 6 ohms. So that's going to give you 12 volts. You have 12 volts there. The other source, the 1 ampere source, would be determined. The voltage for that, the modified source is going to be is equal to IR again, and you assign the values. The current is 1 ampere, the resistance is 5 ohms, and it's going to be 5 volts. Okay, so that's your 5 volt source. Now, I can look at this. You know, this all these components, and at this point, I can determine. You know, I can combine the 2 voltage sources and the 3 resistors and modify my circuit that way. Okay, so let's go ahead and do that. Okay. Okay. So since the polarity of the 2 sources is the same, therefore I have to add them together. I don't have to subtract. So I have 17 volts here, and the 3 resistors are added together, and you have 17 ohms for that. This is 1.5 ohm, and this is 17 ohms, and this is 34 volts. Okay. So now there are different ways you can approach it. One way is that you cannot directly combine these 2 voltage sources. So what you could do is you can combine them if they are purely in parallel. The current sources are purely in parallel combination, and there's no resistor in that branch in which the current source is located, then they can also be combined if they're approaching the same node. So I see the opportunity there where I can convert both of these sources back to by using the source transformation back to current source. So if I do that, this is going to be brought back to parallel. Okay, and since I need to know the current within that 1.5 ohm resistor, so therefore I don't want to, you know, combine this under any circumstance. So therefore this is 17 ohm. This is also 17 ohm. Now I is equal to V over R. So therefore, you know, you have 17 ohm, and so I is equal to V over R, which is going to be 34 over 17. So it's a 2 ampere. So this source is 2 amperes. The second source, again, you have I is equal to V over R. Voltage there is 17 volts, and the resistor is also 17 ohms. So therefore you have 1 ampere there. Let me just label these correct way. So you have 1 ampere. So this is 1 ampere. And when you have this, then I can see that at this node, both the current sources are coming together, so I can add them. In the previous example, I was trying to show you, it wasn't possible to combine this I2 and I1 because there was this resistor in the middle. So that would be an issue. But in this case, you can combine them together. And when you do that, the direction is the same. They're both going towards the resistor. And I'll also take the, so this one is 3 ampere, and this is 8.5 ohm. I'll show you how I got that. And so the 8.5 is the equivalent value. So it is just like 1 over R equivalent is equal to 1 over 17 plus 1 over 17. And again, as I mentioned earlier, when we were talking about the equivalent resistances, a rule of thumb is that whenever the two resistors of same value are combined in parallel combination, the equivalent value is going to be half of that magnitude of the resistance. So, but you can, what you can also just verify this is take 17 as a common denominator. So 1 times 17 is 17, and then this is 1 times 17. So then this becomes 2 over 17. You do the cross multiplication. So you have 2R equivalent equal to 17, and R equivalent is equal to 17 divided by 2 is equal to 8.5 ohms. So that's how we got this 8.5 ohms. But you can also, do just 1 divided by 17 if you feel comfortable. So now I have brought the circuit to a reasonable form where I can easily find my I sub 0, right? So I know that I have a current source here, and then I know this resistor, I know this resistor, and I need to find I sub 0. So then there will be some, let's say, I1 going through this resistor also. So now I can apply the current division here. And to do that, I sub 0 is the source current multiplied by the resistor that you want. I'll just call it R sub 0, or 1 over R0 plus, this is sort of a general form that I've written it. Now you can plug in the values. So this is 3 ampere. This resistor is 1.5 ohms, so it's 1 divided by 1.5, then 1 divided by 1.5 plus 1 divided by 8.5. Okay, and when we solve this, we will have so let's do this. So 3 divided by 1.5. If I multiply this 3 ampere by 1 and then divide, so just resolving this is going to give me 2 in the numerator, and denominator. I have to still resolve this, so it's 1 over 1.5 plus 1 over 8.5, right? If you solve for this, let's go ahead and just open my calculator here. Okay, so okay, so it is 0.784 is the value. So it's going to be 2 divided by 0.7, let's say 85. And when you solve for this, you are going to get the correct value there. So there's another way of, I mean, so this is one technique. And as I mentioned, once you have more and more techniques, you have options to explore. If you want to go with a more simpler option, what you can do is then you can transform the current source and then do the KVL and in that loop and determine the the voltage, or just combine the two resistors and find the current going there. But again, this is going to be your current. So 2 divided by 0.785 is going to be what your answer for this I sub 0 is. Okay, so I'll show you a few more examples in our next session, and then we move on to the R Thevenin, basically the Thevenin and
So the answer is IO equals this 2.55 ohms of resistance.
no, this is current. IO is a current that is flowing through this. So because we are doing current division, so IO is going to be 2.55 amperes.
Amps. Okay.
Yes. Yeah. So that's going to be your answer. Because the resistance value is already known, so we just want to know what the current there is. So that's going to be your answer for this question.
Okay, so we were just trying to figure out what is the current flowing at that arrow that you indicated.
Exactly.
Okay.
So if we sort of go back to our original circuit, I mean, this was directly finding it was a little bit more complex. I mean, you still have to do some analysis. Like if you were to do other techniques that then you have one node here, another node here. So it's if you do nodal analysis, it's going to be a lot of work to solve this problem. But in this case, with the source transformation, it's a lot of steps, but they're simpler steps. So it's
I just forgot what we were doing. Like we were just solving this thing, but like what we're
yeah.
So,
essentially this was the unknown value which we were looking for. But the reason the reason we were doing the source transformation was to find this unknown value. I should have actually explained, find. I just label it here, but find I sub 0. Okay, so that's the whole analysis here. But the goal was to sort of give you an example of source transformation being a good technique to solve this problem. Of course, there are other ways you could solve it. You could do mesh analysis. You could do nodal analysis to solve this problem. But again, it depends on the preference of the person who's solving it. But I think it's much more simpler way in this, particularly in this problem, to sort of bring it. Again, if you brought it to this form here, like after the first step, if you decide that, okay, I have a simple enough circuit here, where I can apply my, I have two meshes and I have two equations, two unknowns. Let me do this. So then that would be fine also. I mean, this I2 of yours is going to be I0. So maybe that would have been a better technique than the route I went. But my focus was to show you different examples of source transformation there. But then again, at some point, you will have different directions to go, all leading to the same result. You know.
Okay, no, this makes sense. I messed up question 4 on the midterm, so
Yeah.
whatever. I mean, just I thought we went over this, and that's why I was like, how do I not remember this? Well, yeah, so
Yeah, it
my homework's
happens.
wrong because I taught
Yeah.
myself this wrong.
Yeah. Okay, so but again, it's a learning opportunity, in my opinion. I mean, it's more important. Okay, so I'll conclude the session at this point, and then next week we'll carry over from this point. And again, I thank you for your participation and taking your time. And I'll see you next Tuesday then. Okay, thank you
Sounds
so much.
good. Thank you.
Mhm.